Hi, everyone. Thanks for joining us today for the Aquatic Animal Health and Dissolved Oxygen webinar. We're happy to have you here. As people are coming in, I'll just go over a few housekeeping items and then pass it over to our presenters, Colleen and John. First off, we do have additional resources that we'll share with you. I'll include a link to a shared Google Drive that includes sample data, the experiment file, and the slide deck from today's session. And we are recording the webinar and it will be available to you on our website, and it will also be sent to you in a follow-up email, which will include a certificate of attendance as well. During the session, we'd love to answer your questions, so feel free to put those in the Q&A or the chat. We'll be monitoring both of those, and we'll do our best to get to your questions. And if we happen to not get yours answered, we will follow up with you afterwards. So I'll pass it along to your host, Colleen.
Good morning or afternoon to everybody, depending on what time zone you are in. So just to kind of go over today's agenda with the talk today is we're just going to give a brief introduction of myself and John. An introduction to dissolved oxygen water, where we're specifically doing an experiment from one of our books called Biology with Vernier, experiment number 19. We're also going to kind of cover a hands-on demonstration of using the pro version of graphical analysis, and one of the great features of being able to data share for that. Then we will have a little question and answer session, and basically make sure you understand how to get your webinar recording after today. So just to start, my name's Colleen McDaniel. I am a biology and environmental science educational technology specialist here at Vernier. What that basically means is I do a lot of things. I do trainings like this, I do webinars. When we were able to be in person, I would do in-person sessions at different schools and go to conferences as well. And when I'm not doing all that, I'm answering any questions that teachers might call in with problems with sensors or how to do experiments. I also do some research and development of creating new probes, and I also do a lot of writing of different lab activities. Just a little background about me. I have a Bachelor of Science in Biology from Truman State University in Missouri. And while I was teaching in Houston, Texas, I worked on getting my master's in science education from Montana State University. And before I taught, I was actually a researcher where I was working on a PhD for a while before I discovered that I like talking to students and people a lot more than fruit flies. So I was lucky enough when I was teaching to be able to teach AP Environmental Science, which, if you do teach that, in my opinion, is one of the best courses in the entire world. And I really, really love teaching that class. In fact, I was actually a grader for a while for the AP exam. I loved it so much. So then we also have Dr. John Melville joining us. I don't know if he would like to introduce himself there.
I'm John Melville. I'm the director of the biology department. I'm a biology staff scientist. I have a BA in biology and psychology. I did my PhD in zoology at Oregon State University, and I did postdoctoral research at the University of Oregon. But the most important thing, just like Colleen brought up, is that I'm a former teacher. So I was an associate professor of biology at a small liberal arts college called Wartburg College. And I've taught majors courses in biology and non-majors courses, and my big focus was on inquiry. But I'm here primarily to support, so if you have any questions, put them in the chat and I will answer them for you.
All right, thank you, John. And so that kind of gets right into it here. You know, we are here for you. So there is a Q&A feature within Zoom. So make sure you answer, if you have any questions at all, throw that question in there. And John and Angie will be answering those as we go. And if time allows, at the end of our session today, we'll discuss any other questions you might have, or maybe any important ones that popped up that we want to make sure the entire group hears. So today we're going to be using one of our applications called graphical analysis. And ideally, we're going to be able to share some data over the internet with you when I've collected it. So if you have your own device, it can be a cell phone, it can be an iPad, it can be the computer or Chromebook you might be watching this on. I would recommend to go ahead and download it if you have it. It's absolutely free. And if you do have it, make sure it's up to date at version 5.9. And that way, later on, when I start sharing my data with you, you'll be able to see it as well and be able to basically have kind of a hands-on point of this webinar for you. So today, the activity we're going to be doing is looking at the amount of dissolved oxygen in water, and specifically look at the effect that temperature has on the ability to absorb the amount of oxygen present. So to do this activity, we're going to be using our Go Direct optical dissolved oxygen probe. And the Go Direct probe is nice because it does not require an interface. It's going to connect directly to a device, be it a computer, Chromebook, or tablet or phone. And it can connect by Bluetooth or by USB. The experiment we're doing today, like I said, is directly out of one of our books, Biology with Vernier. And the great thing about this experiment is, while we're using this probe today for demonstration, if you have any other dissolved oxygen probes, you can do this experiment as well. The only thing is you would also need a temperature probe to do this. So we're lucky that this probe has both temperature and dissolved oxygen readings on it. So we only have to use one probe in this experiment. Well, if you have other types of dissolved oxygen probes, you can still do it. You'll just need to make sure you have a temperature probe as well. And if you have our Biology with Vernier book, all versions of those labs are available for you. If you sign into your account on our website, you can get electronic files of all these and have basically an endless amount of options to be able to use our various probes in this type of experiment. It also allows you to edit the experiment and modify it so that it will fit specifically for what you're planning on using it for and how you want to carry it out in your classroom. So just kind of a brief little introduction here today. So Vernier Software and Technology has now been around for about 40 years. It's our 40th anniversary this year. And one thing to kind of make a point with is that it's for teachers by teachers. Vernier was founded by Dave and Christine Vernier, who Dave was a physics teacher when he started developing his own programming and sensors within the classroom in the 70s. And it kind of developed from there. And next thing they know, Dave and Christine were running a business full time. So 40 years later, we have just over 100 employees. The majority of us, especially in the tech support department here, are former teachers. So we've been there. We know how it is. We know how that, labs can kind of go awry sometimes. And we want to make sure that we have equipment and resources that are going to be best for you. And that the biggest thing is to never hesitate to contact us if you have any questions, or if you want to, run some ideas by us of a lab you want to do, but you're not sure how to start it. That's what we're here for. We are here to support you. Vernier Graphical Analysis is a free app, but there is a pro version that is basically a subscription process that opens up some features that are hidden otherwise. And so the demo we're going to do today, we're going to give you a code that will access those pro features to do some data sharing over the internet. So you don't actually need sensors whatsoever. And that way you kind of can experience it and have access to it for at least a couple weeks. And specifically, we're going to be using that Go Direct optical dissolved oxygen probe. The great thing about that probe, like I said, it's Go Direct, so it's Bluetooth or USB. You don't need an interface. And as an environmental educator, one thing I really like about it is I can measure both saturation and concentration at the same time. And I also have the ability to do temperature and if I want atmospheric pressure. And it's automatically compensated for those as well. So I don't have to calibrate it. I don't have to worry about warm up time. It basically senses the temperature and pressure that I'm at and automatically adjusts that to give me the proper dissolved oxygen reading. It makes really easy water quality measurements. You don't have to worry about any chemicals outstream side or worrying about introducing excess oxygen into the sample. It's super simple and easy to use. And it can be used not only in fresh water, but it can also be used in salt water as well. So there's a lot of people in coastal areas that are interested looking at dissolved oxygen concentration in estuaries or salt marshes. You can do this with this probe, and you can also put in a salinity correction value in there. So we'll actually adjust the dissolved oxygen readings based on what your measurement of salinity is for that body of water. So just a little background here to make sure we're all on the same page of what exactly is dissolved oxygen. When I was teaching, it was really kind of a hard concept for students to grasp because everyone knows the molecular formula for water is H2O. So they immediately think when I'm talking dissolved oxygen, I'm talking about the oxygen that is part of a water molecule. That is actually not correct. What we're talking about is straight O2. Basically the exact same oxygen that is in the air that we breathe, except that it is dissolved in the water. So we're looking at molecular oxygen dissolved in water, not the oxygen associated with the water molecule. And it's important for students to make sure they grasp this because this is the same kind of thing of why we need oxygen in that water, because it's critical for heterotrophs to be able to survive and live in this environment. So where does that oxygen come from then? Well, there comes through some different processes. Primarily, just like in atmospheric oxygen, it can come from photosynthesis, where you have autotrophs in the water that are producing oxygen that is then dissolved and stay within the water column there. You also have the combination process too of diffusion, where when oxygen gas can actually diffuse back and forth between the atmospheric and water barrier. And you can increase that by agitating the surface. So such as a waterfall, ripples, rapids, stirring, shaking, anything like that is going to help increase the amount of oxygen that can diffuse into the water there. And the big thing is there's a lot of different factors that can affect how much oxygen the water can hold. And so some of those can be the amount of salt in the water. So that's why we have different calculations for dissolved oxygen in salt water versus fresh water. You also have to consider the atmospheric pressure, because pressure has the effect of how much gas something can hold onto. And not only does that affect in the atmosphere, it will affect in the water as well. And then lastly, what we're going to be looking at today is temperature. So temperature is one of those key factors that is really easy to look at in the classroom to look at how temperature directly affects the amount of oxygen that can be dissolved into a sample of water. And then the question is, why is dissolved oxygen so important? Well, just like atmospheric oxygen is important for us to breathe, it's important for aquatic organisms to breathe as well. Those heterotrophs are also doing cell respiration, so they need to have oxygen to be able to do that reaction. And as oxygen gets depleted, we're starting to see more and more effects across the globe of areas where there isn't enough dissolved oxygen and the detrimental side effects of this. For example, a popular thing talking about now is a lot of what we call dead zones or hypoxic areas, that there isn't enough oxygen present for fish to be able to even survive. And so this little graphic I created over here kind of shows the general range of dissolved oxygen that we're looking at. Basically, anything that is a concentration of 7 milligrams per liter or above is considered a healthy environment. But if we go too far, too much of a good thing can be a bad thing as well. So if you have water that's hyperoxygenated, it can actually cause some fish diseases as well. So you have to find kind of this perfect balance. Anything below there, you're starting to see some detriment. So at about a dissolved oxygen level of 6 milligrams per liter, some fish ideally kind of trigger this as a spawning event, but it's kind of also at that point where they're starting to not get enough there to be able to fully function. Once we get to 5 and 4 milligrams per liter, they're going to be pretty stressed. They're going to start gasping for air. You'll actually see fish kind of doing the mouth breathing. And then once you're below 3, that's when you're going to have hypoxic sort of conditions and fish are going to start dying. So that's why this is a really important measurement for aquatic health, to give you an idea of what populations of fish can be present and if they're going to be a healthy population of fish or not. So let's play with dissolved oxygen now. So first off, I'm going to launch graphical analysis here. I'm going to make it a little bit bigger so everybody can see it. And what I'm going to be doing is sensor data collection. So I'm going to turn on my dissolved oxygen probe here, and I'm going to click sensor data collection. And here is my probe connected here. So I'm going to go ahead and connect it. And you can see right as I connect it, I have a sensor channel called DO concentration on, which is great because that's what I want to measure here. But I also want to be able to monitor the temperature that's taking place as well. So I'm going to click on sensor channels and I'm going to select temperature so that I'm measuring dissolved oxygen concentration and temperature at the same time. I can also collect saturation or pressure as well, but those are not as important today. So I'm just going to select these two and then click done. The other thing I'm going to do is make my screen a little bit bigger. So I'm going to go into presentation mode here and move our scaling up, that might be a little much, to 1.25. So that way, hopefully it's a little clearer for everybody to see when I'm data sharing. Now, for this lab, what we're going to be doing is basically taking a sample of water and agitating that water and measuring what the temperature and concentration of the dissolved oxygen level in that water is. Now, since we're going to be doing measurements at very distinct points and not over time, I want to be able to change my mode of data collection. So I'm going to go down to mode here and to my data collection settings and click on there. And I'm going to change my mode to event-based, because what I'm going to be doing is telling the software to collect a specific data point at an event that I tell it to. The other thing I want to do here is this great option that's averaging my reading over 10 seconds. And so what this is going to do is when I tell it to take a reading, it's going to take a reading for over 10-second period and then calculate the average of all the readings within those 10 seconds and report that as my value for that measurement point. So it kind of helps take some guesswork out, because a lot of times students will have issues of if you have a little bit of what we call electronic noise going on, where the values are kind of wavering between, say, 7.1 and 7.3. And students are like, I don't know which value to collect, which one to write down. If we take the average of those values, it's going to kind of take away that little guesswork, because a lot of times sensors aren't going to give you a specific straight value. You are going to have some fluctuations, and it helps kind of take some of that anxiety away from the students of worrying about writing the wrong value. So now that I've done that, I am going to click done. And I'm going to switch cameras and go over now to my setup. So for this experiment, what I have is a beaker of ice water. I also have a lovely thermal cup filled with warm water that I will need a little later, and an empty 400 milliliter beaker and a styrofoam cup. Now the empty beaker, I'm going to put the styrofoam cup in, and that's purely for stabilization, to make sure that this doesn't tip over when I do a reading with my dissolved oxygen probe. I also have a lovely 1 gallon jug to shake my water in. Now, this 1 gallon jug is a distilled water jug. You can use a soda bottle, you can use a milk jug. It doesn't really matter what kind of jug or bottle you use. It's just important that you have something that will have a lot of agitation going on to introduce the oxygen to the sample. So first, I'm going to measure about 100 milliliters of my ice water. Put that in here. Okay, and I'm going to pour that into my jug. And then I'm actually going to grab a couple little ice cubes here and put that in there as well, just to make sure we have good cold water in there. Now, once I have done that, I am now going to shake this for 2 minutes. So I'm going to set up a timer and I'm going to start shaking. Now, hopefully you can still hear me while a lot of noise is taking place here. Now, the reason I'm shaking this sample is because I want to make sure that I've introduced a lot of oxygen into it. I want to make sure that it is going to be fully saturated with oxygen gas in this water. Now, like I said earlier, the only way oxygen is getting into water is either by photosynthesis or diffusion. So by shaking it, I'm increasing the amount of diffusion that can take place and making sure that enough oxygen is actually getting in there, and especially saturating it to that point that I can see exactly how much oxygen this water can actually hold at this temperature. The number one thing I see people do with this experiment that they don't get good results on is they don't do the shaking part. The shaking part is critical. A lot of times people will just measure the dissolved oxygen of the water in the beaker. That oxygen level is going to be set no matter what temperature the water is, because you haven't tried to introduce any more. So it's very important to make sure that you introduce the right amount of oxygen in there, and that's how we have to do this agitation process. That's very loud and annoying. So just imagine a classroom of 30 plus students doing that as you're going. All right. So now that it's been about 2 minutes, I'm going to pour my sample into the styrofoam cup. And this is going to act kind of bit of as an insulator as well to make sure I don't lose any of my temperature. And then I'm going to just put the probe directly in there and I'm going to let it sit. And while it's sitting, I'm going to go ahead and start data collection. And I'm going to monitor my temperature here. So I can actually put a meter on so I can look at this closely, and you can see the values are going to be fluctuating here. Now, because the dissolved oxygen probe was sitting at room temperature for a while, it's going to take a little bit for to actually move up and equilibrate at the correct reading. Because it was at room temperature and now we're measuring something that's going to be ice cold, it can take 90 seconds to 2 minutes in order for it to get down to its proper reading. So one thing you can do is kind of stir with the probe to kind of get it going there. And the other thing is just patience. It's really important to let it sit and make sure that it reaches that equilibrium state. The closer you get to room temperature, the less time this is going to take. So the first few times it's going to take a little bit because your sample is so cold. And you can see as I'm stirring, my temperature is going down and my dissolved oxygen is going up. All right, so I think looks like we're pretty stable right now. So I'm going to go ahead, and this is important. As I keep this, remember it's going to average over 10 seconds. So I'm going to press keep, and I'm leaving my probe in the sample until those 10 seconds are up. Because it's taking a reading that entire 10 seconds. And I'm just going to call this event 1, and I am going to keep my data point. So now the next step is to pour the water back into my container here. And now I'm going to shake it for another minute. And so the idea is you're going to basically shake it for a minute and then do a reading. Shake for another minute and do a reading. And as you're shaking, what's happening is you're making sure you're introducing, like I said, enough oxygen by diffusion. At the same time, the basic friction of shaking the water along with being in room temperature, you should be seeing the water start to get warmer as well. So the idea is after every event, you're going to get a measurement and you're going to see the temperature should get warmer and the dissolved oxygen reading will change as well. And that will kind of at the end give us an idea of this relationship between dissolved oxygen and temperature. Okay, it's been 1 minute. And put my sensor back in. And again, we want to make sure we get to a point where this is stabilized. And we can already see our temperature is quite a bit warmer. And we watch those values and make sure they're fully stable. Okay, so I'm going to go ahead and press keep. Let it sit for 10 seconds. And event 2. All right, then I repeat the process again. And we're going to keep doing this until our water reaches basically the equivalent of room temperature. So I start my timer again and I keep shaking. Now, this is going to be the last one I do for the cold water, just for sake of time, because I don't want everybody to just stare as I shake water. It's not very exciting moment of here. So once I'm done doing this, and usually it'll take possibly 5 to 8 trials, depending on what the temperature of the room is. The idea is you want the temperature of the water to reach about room temperature. So that can be anywhere between 22 and, well, 25 and 35 degrees Celsius, basically. 35 is still pretty warm, but so it's probably going to be closer to about 25 degrees Celsius of what we're looking at. Right. Minutes. And do a measurement. And you can see with my optical dissolved oxygen probe, I don't have to worry about putting it back in water to store it between readings. It's really stable outside of a humid environment, which is nice. So for short-term intermediate with a lab like this, you can just, the students can just lay it on the table and just kind of use it as is. If you have a regular dissolved oxygen probe that requires filling solution, for example, that one does need to be placed and stored in water between each of these data points we're collecting. Okay, so it looks like I'm pretty stable. So I'm going to go ahead and keep my data point now. Now, the next thing I want to do is I'm now going to, so we're starting with cold water and moving down. We're starting with cold and moving down to room temperature. So that's going to kind of cover our cold end of the spectrum. Now what I want to do is start at the bottom end. So I'm going to add warm water and start going up to room temperature that way. So I'm going to measure it going from warm to cooler room temperature. So to do that, I'm going to remove about 25 milliliters of my water sample that I currently have. And I'm going to replace that now with warm water. And so I'm going to pour the warm water and the cold water into my container and shake for another minute. Now I can see the temperature of the water I have here. Ideally, you start with water that's around 40 to 50 degrees Celsius. This I just took from the tap and put it in an insulated mug. And this is where the dissolved oxygen Go Direct probe comes in handy because I can use it to look at the temperature of this water as well to kind of get an idea of where I might be with it. As I'm shaking. You can see it's fairly warm, so that's a good temperature to go with. All right, it's been a minute. Pour my sample in. And let's see what we've got now. So letting that kind of reach that equilibrium where we're having the temperature is having to go to a warmer state than what it was, or in this case, in a way, a cooler state because I had put it in my warm water sample to begin with. And so I'm letting it reach equilibrium. And then once it's kind of reached that happy point, gonna go ahead and press keep once I see those numbers stop moving in a specific trend direction. So since my dissolved oxygen concentration is still going up and my temperature is still kind of trying to find its happy point, I'm not going to press keep yet because I want to make sure that we're done with those general trend of movement. So I'm looking at this value, see it's still going up. If this number kind of starts to stay the same for a while, then I would go ahead and press keep. So we're kind of slowing down now. So it's pretty stable now. So now I'm just going to go ahead and press keep because it's taking the temperature's not moving anymore. And that's where it's nice. You can do this average over 10 seconds. So it kind of takes some of that guesswork out of, oh, when should I collect this data point? So this is going to be event number 4. And we're going to do this one more time. Get my lid. Start my shaking for another minute. Remember, as we're going through this, if you have any questions, please don't hesitate to put them in the Q&A section. Sample in. And I'm going to have this be the final reading that we're going to do. Okay, so let that kind of stabilize. And it's looking fairly good. Oh, still moving. All right, I'm going to go ahead and do my averaging over 10 seconds. And this is point number 5. So I'm going to go ahead and stop data collection now. And so when I'm looking at this graph, what I'm right now seeing is just dissolved oxygen concentration over our events. But I really want to look at is this relationship here. Now, what I'd like to do is share this also with you. So what we're going to do is I'm going to activate Graphical Analysis Pro. So I'm going to unlock the feature set by using a code. And this is going to allow me to actually do some data sharing where I can share the data over the internet with you, and then you can do your own analysis of the data we've just collected. So the idea here is this is kind of a situation that becomes ideal for if you have a hybrid situation where some students might be in person, some might be at home or remote and being in at Zoom, so they can still participate in the lab activity. This is also a great way for you to do a demonstration and then share that data out to the students so they can do their own analysis to kind of demonstrate their own level of understanding. So in order to do this, we need to make sure we have activated the Pro features. And in order to do that, we need to enter this code, oops, right here. So I'm going to open my graphical analysis. I'm going to make it a little bit smaller so I can see the code and my screen at the same time. I'm going to go to the other options button and do about, and here is where I can enter my code. So I'm going to enter IB3EW39F7. So you want to enter that, and I'm going to submit it. Oh, guess that was not.
Is it a lowercase L?
That might be a lowercase L. Thank you. Thank you, John. We'll submit that one. There we go. So this activates a subscription that is going to be good through August 16th. And so once I've done that, I have this lovely thing that lets me know how long it's active for. I'm going to close that little warning there. Now, once you have entered that code into your graphical analysis, what you want to do is hold on, let me save this. Onto the desktop. When you go to new, well, let me first activate a sharing session. So there's this little data sharing icon here that I'm now going to turn on and start data sharing. So there's basically two codes that need to happen. One is the code to activate the pro features of graphical analysis. The second is the code that you're going to need to enter for data sharing. So here's your code, DJR1ZO, not 0, O. So what you want to do is go to new experiment, and you're going to select data sharing. And when you go to data sharing, there's this online data sharing feature, and this is where you want to enter that code I just shared. And then you'll click connect. So I'm going to go ahead, open this up again. So this is the ID you want to select. And it's nice is it actually tells me right here, for example, that I have 2 clients connected. So there are 2 people that are currently connected looking at this data set. Now we have 3. So it allows you to see that there are students connected and actually looking at the data you're sharing. So now we can go into our own analysis phases. So specifically looking at this experiment, we're looking at that relationship between dissolved oxygen and temperature. So I want to change my axes because I don't care what my dissolved oxygen was for each event. What I care is what was the concentration for each temperature reading. So I'm going to change my x-axis here to read temperature instead. And so now I get the graph that's showing the relationship between dissolved oxygen and temperature. Now, here's the great feature of when you're sharing these data sets over the internet is that you're sharing the data itself, but any analyses you do are not going to be shared. So now students can have their own copy of this data and from here be able to do their own analyses. So for example, if you want to ask students, what is this relationship that's between dissolved oxygen temperature? What we can do is add a curve fit. So I can go in here, I can apply a curve fit, and I can put this linear fit onto my data. And here I now have my linear fit information, and it shows me that there is a direct relationship now between dissolved oxygen and temperature, and that the higher, it's basically an inverse relationship where the colder the water is, the more dissolved oxygen it can handle. While the warmer the water is, the less dissolved oxygen the water can hold on to. And so you can have students now with this curve fit kind of answer some questions of, well, with this, what happens if our water temperature increases or decreases by 5 degrees? What's going to happen to the dissolved oxygen concentration in that? And so students can go through this and start answering some questions and thinking about how this affects specific environments that they might be looking at. So for example, if we think about the Gulf Coast and the temperature of the water that's coming out from the Mississippi River there in the Mississippi Delta, what happens if that water temperature goes up 2 degrees or even up 10 degrees? How is this going to affect fish populations in those areas? Students can also go into further research of looking at different streams and the different types of oxygen levels that are required for specific species of fish. And look at, if you want to have an ideal trout stream, you're going to need a very high dissolved oxygen level. So if we start thinking about climate change and surface water is starting to get warmer, how's that going to affect trout populations? And then kind of basically go on beyond that and look at, well, if that affects trout populations, what other animals rely on the trout? How is that going to affect those populations as well? And then kind of start asking a lot of different questions about how does this affect various factors of the environment and ecosystems, even though we're just looking at one specific value of water quality. So what we can do now is I can then stop sharing. Once I have all the data out there, when I stop share it, is everybody will still have that data available to them, and then they can save that data and further manipulate it later on. So we have the other features. I just kind of want to show a couple other features here of Graphical Analysis Pro that are available to you. You might have seen when I go to apply curve fit here, you have the ability in Graphical Analysis Pro to create a custom fit. So if you want to create your own fit equation, you have the ability to do that here. The other thing that we have ability to do is that we have some sample experiments that we have actually embedded into the GA Pro license. So when we go into the experiments here, we actually have a list of sample experiments that are available. So for example, let's see, this one isn't present, but if I want to say, look at cell respiration. So I can download this from the cloud, and then I can run this experiment. And not only do we have the data for this experiment, but we also have a video to go along with it that also shows the process of the experiment taking place. So it will run the experiment here and show the data live as well as it's taking place. So I'm just gonna I can fast forward through here. I can speed this up. So it goes nice and quick. And once it gets to a point, it's going to actually have the data graphing live as the video is taking place. This also is an ability of something that you can do. You can record the video and collect the data and have them sync up in the application at the same time so that students can also have this viewing and see the experiment actually taking place while data is being collected as well. And this is a great feature, especially for student absences. For example, if a student misses a lab and they need to make that lab up, this is a lot easier and less time consuming for you to be able to do something like this instead of having to find time outside of the school schedule for the students to come do makeups. All right, so there we go. So we're kind of at the end of our presentation here. If you have any further questions, don't hesitate to ask them. Like Angie said, you will get an email with a link to this webinar recording. It will also be posted on our website as well. And you can just basically refer to it at any time that you want to measure there. So I'm just going to go through and take a look at any questions we might happen. So let's see here. I'm actually looking at a couple ones just so people are interested in some questions, some good questions here. So one person was asking a question about salinity. Do you have to calibrate for salinity? And so salinity, it's basically a correction factor in there. So if I pull up and do a new experiment again, and my probe should still be connected. So if I go to my sensor channels here and turn on DO salinity, what this is going to measure is I need to go into calibrate here, and I'm going to enter the salinity value. So it doesn't measure the salinity itself, but you need to know the salinity of your sample and then enter that value in here. And then the probe will automatically do a correction to correct the dissolved oxygen reading for that salinity in which it is reading. Someone asked if you once we put the water into the container, you do want to seal it. So basically, and it's more to just make sure the water isn't flying out everywhere. It's not a matter of keeping that amount of oxygen in the container itself. So yeah, so someone asked, would you see problems with jumping around with the temperature? Two groups using the same probe, one group working from cold, one group working from warm. You wouldn't necessarily see a problem with that, but what you might see is it'll take longer for that temperature to reach stabilization and kind of an equilibrium, basically. And it's purely because the probe is temperature and pressure compensated that, let me stop sharing here. So since the probe is temperature and pressure compensated, you will see a problem. It won't be a problem. It'll just take more time for it to reach that kind of equilibrium of that temperature for that reading and in that environment. And lastly, in the field, can the probe measure DO differences between a warm pond versus a cooler stream? And yeah, you can do that where you can be in the environment and kind of look at differences. I was out in the field once and did for an overnight workshop I did. And there was an area that had basically almost like little vernal ponds that were forming because of water levels of being high or low. And so I measured the water, the dissolved oxygen in the water first thing in the morning, and was having a dissolved oxygen level about 4.5 milligrams per liter. And then I came back 6 hours later after it had been sunny all day and measured it again, and it was up to 9 milligrams per liter. And that was purely what I saw a difference of the water did get warmer. And also there was a lot of algae in that water that were doing lots of photosynthesis that were adding oxygen that wasn't there after the nighttime during the dark cycle. So you can definitely use the environment for this type of experiment as well to kind of draw those conclusions. It's actually, in my opinion, it's more fun to do that because you get to be outside and do that. But I know not all classes necessarily enable that. For example, for environmental science, it's super acceptable and easy to do that. For AP biology, it might not be as easy to go do that. So there's this very simple activity that can be done in the classroom to be able to do this type of measurement for that.
There's one other question, Colleen.
Uh-huh.
Can one device record measurements from different locations using multiple probes?
Sadly, no. So you're not able to basically have these throughout the lab and all be reading, or through different field areas and reading to one place. They all will be individual because it's Bluetooth. It has to be a direct connection on site. So you would have to basically collect data points at different locations and then come back together and then compile those by hand into a data table yourself. You are able to export this data as a CSV as well with the Pro feature. So you can actually be able to do certain analyses in Excel or compile data and put, if you have GPS coordinates, you can put them out into Google Earth or ArcGIS as well. Well, thank you all for attending today. We really appreciate it. And don't hesitate to reach out if you ever have any other questions. You can reach us at biology@vernier.com through email super easily, where you would either talk to me, John, or our other biologist, Sarah, or just support@vernier.com as well. You can also reach us by phone, or we also have a chat option now on our website. So we are here to help you, and don't hesitate to ever reach out, contact us, and give us a ring, even if you're bored and want to give us a talk. Thank you all, and I hope you have a wonderful rest of your day.